Magnetic induction makes the world turn from electric motors to induction cougars. But have you ever heard of dielectric induction? Dielectric induction is the electric counterpart of magnetic induction. It is the working principle behind a capacitor. While magnetic induction is based on changing current, dielectric induction is based on a changing voltage. So it is based on a changing dielectric field instead of a changing magnetic field. And this has benefits. For example, with dielectric induction, there is no Lenz law. My name is Ivo and I'm open source researching Nikola Tesla's bifilar pancake coil and his impulse electricity. Let me now explain and show you with two experiments how dielectric induction works. This is a new chapter in my open source research. I have now started researching current impulses that are made from capacitor discharges. I will give a short overview of what is happening. Later in this video, I will go deeper and deeper into detail. I use the fast charge and discharge of a capacitor to produce both polarity current impulses, whereby an inflow and an outflow of energy is created in the form of a displacement current. To produce these two current impulses, I need to quickly charge and ultra-fast discharge a capacitor. To get this discharge to be ultra-fast, I need a low resistance shortcut. Nikola Tesla used a spark gap for this, which is suited for very high voltage discharges. But I used parallel MOSFETs that can share the extremely high capacitor discharge currents. My discharge voltage will thus be limited, since parallel MOSFETs are limited in their maximum voltage. So I need to get the voltage of the capacitor discharge higher to get a decent effect. And I have designed a brand new circuit that uses resonance to increase this capacitor discharge voltage. To be able to do all this, I use bifilar pancake coils that act as capacitor plates. Let me now explain some of the circuit basics before going deeper into the experiments. The MOSFET switch will only discharge a relatively low voltage capacitor with low energy, but this small discharge is part of a much higher resonant voltage of a special capacitor. This special capacitor is only partly discharged, and due to the much higher voltage, the capacitor discharge energy is much higher. This is because the energy increase in a capacitor is related to the square of the voltage. When the voltage, for example, increases 10 times, then the energy increases 10 times 10 is 100 times. This means a small change in voltage will have a much higher change in energy. This is very interesting, as this means the MOSFETs only deal with small amounts of energy, while at the same time it sets much larger amounts of energy in motion. Let me now explain this further. So here are two bifilar pancake coils. If I hold them together, they form the plates of a capacitor. But at the same time, they're still coils. So I call this a coil capacitor, which reminds me of Doc Brown's flux capacitor from the 1985 movie Back to the Future.
I had a revelation, a vision, a picture in my head, a picture of this. The flux capacitor.
This special capacitor can be DC charged by giving one of the plate coils a DC voltage, while the other plate coil stays grounded. If I then quickly discharge the voltage of that one plate by connecting it to ground, this fast voltage change produces an intense longitudinal displacement current. As a result of the changing voltages, the plate coils of the coil capacitor will become resonant. But there is more going on, which I will explain later in this video. Now, to increase the voltage difference between the plates, I flip one of the plate coils over. As a result, the dual resonant coils will now be 180 degrees out of phase, which increases the voltage difference of the coil capacitor plates. Here's the L2, L3 coil capacitor, whereby L2 acts as one plate of a capacitor and L3 acts as the other plate of a capacitor. And they together can charge up a dielectric field in between the plates. Now, this is not only a capacitor, but it's also a close-coupled coil. And if you take a closer look, then you can see that L3 is clockwise from the inside to the outside, while L2 is counterclockwise from the inside to the outside. In other words, I flipped the L3 coil over, so it is counter-rotating. And this is done so that the resonant voltages of L2 and L3 will be opposing, will be 180 degrees out of phase, which means that when L2 reaches its positive maximum, the L3 will reach its negative maximum. This will be the zero line, so we've got a positive and a negative maximum, which will have a very large voltage difference between them. And this voltage difference is creating a dielectric field which charges up the coil capacitor. So here the inside rims are open-ended, and that is where the resonance takes place. And the outside rims are grounded on Earth, but L2 has a capacitor through which it is grounded to Earth. And this capacitor is causing L2 to have a DC offset, but it is not constant. This capacitor is being charged up and discharged. So we have a charge up and a discharge, as this is the zero voltage and here is the negative voltage. And this discharge is very, very fast, causing a very strong displacement current between those coil plates. Now, to use that displacement current, I have created parallel capacitors over them. So here is a small capacitor parallel over the bifilar coil, and here is a large parallel capacitor over the L3 coil. And this causes the L3 parallel resonance to have a very large impedance. And that large impedance causes the displacement to not be able to flow. And it more or less creates a vacuum in that capacitor. And that vacuum is balanced out by the earth ground, which provides the displacement current into the L3 plate coil. And that makes it amplified in its resonant energy. So there is a lot more voltage and current in L3 than would be expected. Now let me show you step by step how this works with my new circuit. First, let's take a look at how I charge and discharge the small capacitor. To start, you need a DC power supply, a MOSFET switch, a coil, an ultra-fast diode, and a small capacitor. this is the basic circuit. We've got a positive and a negative power supply DC, of which the positive DC is earth grounded. We have a switch in orange. We have a diode. We have a coil, L1. And we have a C1 capacitor of 2 nanofarads. If the switch is closed, then C1 is shorted out, but the magnetic field of L1 will build up due to the supply of voltage. Thus, it will produce a magnetic field, like this red spiral. That means there is energy in the fields around that coil as long as that switch is closed. When the switch is turned off again, the coil will shortly become resonant, but only for a quarter wave. And it will charge up the capacitor parallel to the MOSFET switch with a negative voltage dielectric field. And that is the first current impulse, which is relatively slow. Now the switch is opened, the orange one is not conducting anymore. Now L1's magnetic field has no right to exist anymore. So that field energy will transform due to resonance. So it will produce a negative voltage drop, which charges up the C1 capacitor with a negative voltage. So that L1 powers up that C1 with a dielectric field. And once C1 is charged, we've got a stable situation again. There will be no change. To prevent this coil and capacitor from staying resonant, a diode is placed between the coil and the capacitor. This diode prevents the capacitor from discharging back into the coil, so it needs to be very fast. So the resonance already stops after a quarter wave, whereby the voltage in the capacitor stays negative. So that voltage would continue to be negative on C1. If the MOSFET switch is now turned on again, this capacitor will be shorted out and discharged through the MOSFET switch. So now the switch is closed again. The orange line conducts again and will charge the coil up. But more importantly, C1 is shorted out through that switch. So the voltage over C1 drops to 0 because it was a negative voltage and now it will be 0 volts again, equal to earth ground. This is the second current impulse, which is much faster due to the absence of inductance. The capacitor discharge will produce very high currents through the switch, but luckily only for a very short amount of time. So if we open and close the switch, we will produce what is called a square wave. And it actually isn't quite a square wave because the charging of C1, this red part, is dependent on the resonant frequency of L1 and C1, which will be a quarter wave resonant. So there's a quarter wave of resonance, which is a current impulse. And that is a little bit slower than the discharge, because the discharge happens through this circuit, which is a short circuit, which has very low resistance and very small inductance. It is a straight discharge and it is very rapid. So this discharge is much faster than the charge. The charge time can be 700 nanoseconds, depending on how big the inductance of L1 is and the capacity of C1. But the discharge will be much quicker. It only takes around 60 nanoseconds. That means the capacitor discharges in 60 billionth of a second, and that's really fast. The result is a very rapid change in voltage in a very small amount of time, which we will use for dielectric induction. As this fast change in voltage creates the strong longitudinal displacement currents. Since the charge speed of the capacitor is slower than the discharge speed, it means during the discharge there is more energy flowing into than that there is flowing out of the conductor during the charge of the capacitor. Let's take a look at this charge and discharge speed in the first experiment. Here are my parallel MOSFETs. So these are two stacked MOSFETs. They are matched in their gate source threshold voltage to be able to switch on and off simultaneously. This is important as they need to share the high current load. On that PCB I have soldered the capacitors 3 times 330 picofarads per board. So in total almost 2 nanofarads of capacity. This is the coil L1. It is a speaker wire coil and it is wired unifilar. So the two windings are joined together at the start and the end of the coil, making a single winding. Here is the power supply. It's 3 microfarad capacitor parallel to the power supply because it will deliver the currents that will charge up the coil with a magnetic field. It is grounded on the positive voltage, so that's the earth ground. And here is the diode in between the L1 coil and the MOSFET switch and the capacitors. I will probe the capacitor at the source of the MOSFET. So this will read the voltages of that capacitor. I'll now turn the system on. I'm at a frequency of 70 kilocycles per second. If you now look at the scope, the green line is the voltage probe with a setting of 50 volts per division. And underneath in blue, purple is the square wave that drives the MOSFETs simultaneously. We'll now increase the power supply and we will see the square wave being produced. As you can see, the voltage is charged up to a negative value. So we have a negative voltage in that capacitor that is being charged and discharged. 250 volts. Well, this is a beautiful signal. Right now the power supply delivers 0.47 amps at 14.6 volts. I'll make a screenshot, turn the system off. First we're gonna take a look at the charge. So this is the charge. You might be a little bit confused because it's going down, but it is a negative voltage. So I have now set this to 200 nanoseconds per division. I'll turn on the cursor. I'll set one marker here where it starts charging, and I'll set one marker around here where it has reached its charge. And we can see now in the bottom right corner that delta T is 654 nanoseconds. So that is the amount of time it takes to charge up this capacitor of nearly 2 nanofarads to a voltage of around 250 volts. Now I am going to look at the discharge. And the discharge is through the MOSFETs, the parallel MOSFETs. And you might already be able to see it. It is much faster. I'm now at a time scale of 20 nanoseconds. Let's go even further, why not? So now the start point and the end point is a little bit more vague. I would say here it is discharged and here it starts charging. So that measures out to be around 60 nanoseconds in discharge time. So that is 10 times as fast discharging than it is charging. Now a high frequency voltage square wave of several hundred volts is produced, whereby the charging of the capacitor to a negative voltage is slower than the discharging of the capacitor back to ground voltage. This means that the biggest displacement current will occur during the discharge of the negative voltage back to ground. So, To be clear, these rapid unipolar changes in voltage are current impulses. And these current impulses create unipolar displacement currents, which means there is an energy movement in a single direction into or out of the conductor. I have made a short video that explains this. Let's take a look at it. This is a capacitor, which has two plates. When the capacitor plates have different voltages, a dielectric field exists between the plates, which holds the electric charge energy. When a shortcut is created with a wire over the plates, the non-conventional real magnetic current flows from the negative plate to the positive plate. At the same time, to close the circuit, a dielectric displacement current flows from the positive plate to the negative plate through the dielectric material between the plates. Together, these two different currents close the circuit. What is important to realize is that when the negative plate suddenly becomes positive, the energy flows into the plate from the ambient medium. This is the coil capacitor. It is made of two bifilar pancake coils that are closely stacked together. And I've cast them in epoxy because that is a good dielectric and holds them in place. As you can see, it is red on this side and it is red on this side. And that is because one of the coils is flipped over. That makes it out of phase. Let me now measure the capacity of this coil capacitor and the inductance of the two coils. I have now connected it to the outside rims of both bifilar coils, and I'm measuring at a frequency of 100 kilocycles per second, and this gives us 560 picofarads of capacity between these two bifilar coils. I have now connected it to one coil on the outside and inside rim and now measure the inductance. I'm now measuring 302.4 microhenries for the L3 coil. Now I'm gonna connect up the other coil, L2, outside and inside rim, and measure its inductance. And this one is 310.2 microhenries. The second experiment. I will now place the coil capacitor in parallel with the C1 square wave capacitor. The two plate coils are completely identical, and when coupled they form a capacitor of around 550 picofarads. This coil capacitor is very special because it is a capacitor and a coil at the same time and space. Now I have extended the capacitor plates of C1 by L2 and L3, which together is the coil capacitor. So this plate is extended by L2 and that plate is extended by L3. So these coils, which are pancake coils, are actually acting as capacitor plates which are parallel to that C1 capacitor. This means that C1 now is a little bit bigger in capacity by adding those plates. So L2 and L3 will also be charged and discharged, and because there is field energy being charged and discharged here, these coils will be able to become resonant. The resonance is used to not only raise the voltage, but also to increase the currents. But to do this at a low speed, we need to tune the resonance down by adding parallel capacity over L2 and L3. So here is a capacitor. Parallel to this primary L2 coil is a C2 tuning capacitor. This capacitor will tune the resonant frequency of L2, giving plenty of resonant voltages on the inside rim of the plate coil. Thus, the characteristic impedance will be tuned to the high resonant voltage side and a low resonant current. And here is also a capacitor. The second plate of the coil capacitor is called the L3 secondary coil. It is earth grounded on the outside rim. And again, parallel to the secondary L3 coil is the C3 tuning capacitor, which is larger, and it will drastically increase the impedance of the L3-C3 parallel resonance, which is important for this to work. More on this later. So now we have a coil capacitor that will become resonant. For clarity, I will give a dot here and a dot there and a dot here to clarify the inside rims and the outside rims of the coils. Now L3 is grounded with its outside rim on earth ground. Now C1 is 2 nanofarads, just like before, and C2 will be equal in size, also 2 nanofarads. But C3 will be 8 times larger, 16 nanofarads. And still, these coils will have the same resonance frequency. Now, how can that be? First of all, they are close coupled, so they have mutual capacity, but also mutual inductance, which means that their magnetic fields are entangled. And this C2L2 parallel resonance will want to go in a very high frequency due to the relatively small capacitor. And the C3L3 parallel resonance will want to get to a much lower resonant frequency because that 60 nanofarads takes a lot more time to charge up. But we can use harmonics of these frequencies and tune it to a much lower frequency, whereby the C3 is at a subharmonic of C2. Let's take a look at the waveforms L3, and we take a look at the waveform of which is 3 times higher. So now, in this period of time, instead of 1 wave, now we have 3 waves. 1, 2, 3. So this is its third harmonic. It has a frequency 3 times as high as L3. 1 wave, 2 wave, 3 waves, while L3 only has 1 wave. So this is the third harmonic, whereby the waveform perfectly fits inside of L3. Now this means that the L3-C3 resonant capacitor and coil has a very large impedance due to its parallel resonance compared to L2-C2. And that is very important, because when that switch is closed and C1 is being discharged by the shortcut, the same will happen here with L2 and L3. These act as capacitor plates and they want to discharge, but they are also resonant. And this will hinder, due to its large impedance, a sudden change in voltage, which wants to happen through the shortcut. So that large impedance hinders that voltage change and creates an imbalance which will need balancing out. And it will be balanced out by earth ground. In theory, this will change the characteristic impedance of L3-C3 towards favoring high resonant currents with lower resonant voltages. But this will not hold up in practice. Not only the current, but also the voltage will be high. And that is truly extraordinary, as the energy is coming from somewhere else than the power supply. Now, earth ground will produce a displacement current into that resonance system of L3 and C3 to balance out that energy vacuum. And by doing so, it will increase the resonant energy of L3 and C3. So we now have an influx of energy, and that is a displacement current that is feeding that resonance system of L3 and C3, which increases the voltage and increases the resonant current. So the coil capacitor is placed in parallel with a small C1 capacitor. The C1 voltage square wave, which we have seen in the first experiment, will now also charge and discharge the L2, L3 coil capacitor. So the L1 will charge up the coil capacitor and the MOSFET switch will discharge the coil capacitor. And in this charge and discharge process, the coil capacitor will become resonant. The coil capacitor will not be fully discharged, but the energy displacement in the field will be much larger since the voltage is so much higher from being resonant. Okay, I have now connected the coil capacitor, so the two coils which form the capacitor, and I place the L1 coil to the side because I do not want magnetic coupling here. I want to show you dielectric induction. Parallel to the L2 coil is this capacitor, which is equal in size to the capacitor which is in parallel with the MOSFET switch. So 6 times 330 picofarads makes 1980 picofarads, near 2 nanofarads of capacity. The L3 coil is grounded on the outside rim, and I have not connected the capacitor to the inside rim of L3. So it's free to resonate, it has low impedance. I'm now going to show you the voltage sign of the L2 with the yellow probe on the inside rim of L2, which is resonant, and the green probe will be on the square wave of the C1 capacitor. I will now turn the system on and show you the oscilloscope. The system is now turned on and the power supply delivers a current of 0.85 amps at 25.9 volts. I made a still shot of the scope so I can turn the system off again. And we see in yellow the voltage of L2. Let me turn off the green, which is the voltage of the C1 capacitor. So this is the voltage of the inside rim of the resonant L2 with its parallel capacitor of nearly 2 nanofarads and its series capacitor of nearly 2 nanofarads. As you can see, it is now at a subharmonic of 3 octaves below because we have 3 sine waves in total per period. So here is one period in the blue on and off of the MOSFET switch. We can count, this is the low, 1, 2, 3 periods per period of the MOSFET switch. So this would be driven best at 3 octaves higher, which would be 3 times 55 kilocycles per second. But I do this specifically. It needs to be a odd harmonic because we're charging and discharging the capacitor. So here is the discharge, and this is where the MOSFET is being turned on and it shorts out the capacitor, so it creates this sudden shift in voltage. And this balances the resonance of L2 to be grounded on earth ground, so it is now higher. And then here is the charge. When the MOSFETs are turned off, L1 produces the impulse and it charges up that C1 capacitor, and then it stays charged, and the L2 resonance will have a DC offset. So now it is ringing at a DC offset of that negative charge of that capacitor. Let me clarify that by introducing the voltage on the source of the MOSFET. So this is the voltage of the parallel capacitor on the MOSFET, C1. It is 0 volts, then it is charged up, and then it rings along with the resonance of L2. and then it is discharged again. So the charge voltage looks higher. It is 1, 2, 3, 4, almost 500 volts negative, while the discharge is only 1, 2, 300 volts. This is because that capacitor becomes resonant with the L2 coil. So L2 is now both series and parallel resonant. It is series resonant with C1 and it is parallel resonant with C2. And both capacitors are equal in size. So I now connected the tuning capacitor to the L3 plate coil. And this creates a large impedance because the capacity is much bigger than the L2 capacitor. C2 is 2 nanofarads, but C3 is 25.3 nanofarads, which is much larger and gives a much higher impedance to L3. So it resists the change in energy. So I would expect to have a large current in L3, but not a high voltage due to the high capacity. Let me again turn the system on. And here is the signal. Okay, the system is now still at the same power level. The frequency, I tuned it to 55.14 kilocycles per second, which is almost the same as before. In yellow, the L2 inside rim, and L3 inside rim is now in orange. Both channels have a 200 volts per division. Now what you can see is that L2 does not show a perfect sine wave and it is a little bit wobbly. In orange we have a voltage of 793.65 volts peak to peak, and that is exceptional high for a capacity that is so large. We have 25.3 nanofarads parallel to L3. So how can that be so high? The energy must be coming from somewhere. Anomaly. What was to be expected is that due to the increased capacity of C3, the resonant voltage of the L3 secondary would be much lower. But instead, it is still relatively high. There is a significant increase in energy in the resonant L3 and C3. The source of this energy is the earth ground. Let me show you this with a current probe. So this is my current probe. It's a Pintec PA655, which is 500 kilocycles per second rated, and I'll put it on the 200 millivolt per amp setting, and the arrow will point towards the coil, and I'll hook it up to the L3 inside rim, like so. Now the probe is set to a AC measurement, so let's take a look at that current in that L3 coil. I'll turn the system on again. So now we see the current of the inside rim of L3, and it shows a current of 6.6248 amps peak to peak. What you can also see is that it is not a perfect sine wave. It is a little wobbly, to say the least. So now in yellow we have the L2 voltage, and you might see some similarities on the wobbly current of L3 and the wobbly voltage of L2. There seems to be a correlation between the fluctuations in both those measurements. And this indicates to me that this is actually not a magnetic current that I'm measuring in L3, but actually a displacement current, which is related to the changes in voltage of that coil capacitor. Now the question stays, where does that energy come from? And therefore I will now probe the earth ground. Now to be clear, this whole resonance system is only grounded on one point, and that is this earth wire. And I've now put my current clamp on the earth wire. So the earth ground is being probed for the current. I removed all other earth grounds from the system and they're all connected to that single wire. And now we're gonna take a look at the current through that earth ground wire, which should be 0, but it isn't. That's where the energy is flowing. Let's take a look at the oscilloscope. I use the same power settings as before. So this is the current of the ground, which is not supposed to be flowing, but it is. And if we take a look at L3 and compare it, then we can see that it has a different frequency. This peak is 1 and this peak is 1, but we have 1, 2, 3 times the frequency of the single L3 sine wave. And that corresponds with the frequency of L2 by itself. Now let's take a look at L2 and compare it with the current again. And now L2 in yellow comes in. We can see here is the discharge when the MOSFET is conducting, and here is the charge when the MOSFET opens up the switch. So between the charge and the discharge there is 1.5 wave, and again 1.5 wave. So that corresponds with that frequency of the L1 coil, which I tuned before to the 3rd sub-octave. So switch is turned on, switch is turned off, and we have 3 oscillations in that period. And that is the ground current, which is very odd to me, because the L2 isn't at that frequency anymore. So where does that frequency come from? Now this is rather unique, and it is caused by the fast change in voltage of the L2 plate. The L3 plate is close coupled to L2 and wants to react to this voltage change, but due to its high impedance, it can't. So there is a vacuum of energy created, which is a form of implosion. And nature responds to this imbalance by providing energy. And this energy vacuum is balanced out by earth ground, which supplies the needed displacement current energy into L3 and C3, which amplifies the resonant current and voltages of L3. Thus, an energy pump is created, which draws in energy from the surrounding ambient medium, the Earth. Conclusion. So we have an unbalanced capacitor by giving both plates unequal amounts of surface area, whereby the small plate changes voltage very rapidly, while the other large plate resists this voltage change because it has a higher impedance. And the imbalance which this creates is balanced out by nature, providing the needed extra energy to create balance in the form of an inflow of displacement current. So, by using dielectric induction, large displacement currents are created that create an inflow of energy into the resonance system, which produces high resonant currents and voltages. Dielectric induction works without using magnetic induction, so there is no Lenz law, which is a great benefit. So this is an example of how plate coils can be used to create resonance by using dielectric induction. And not only that, it creates an inflow of energy from outside of the system. And this is the next chapter in my research. The high voltage square wave are actually 2 current impulses that induce positive and negative displacement currents. If you want to support my open source research, you can do so by leaving a donation on my PayPal account, which is listed below. Thank you for watching and see you next time.